Not anticipating having it going again for another hour or whatever. Yeah. All right. You guys want to start with some questions from homeworks? Go. 23. Sure. All right. So for number 23, it asks us to prove that u dot v is equal to v dot u. So for any of these, what I'm going to do is kind of denote them in a component form. So u dot v then is going to be u1 u2 dot v1 v2, and the formula for dot product is the product of the x components plus the product of the y components, right? And now remember, u1, v1, those are just real numbers. They're not vectors. They're just like 5 or 6 or 12 or like a regular old number. And I know the order in which I multiply real numbers doesn't matter. So u1, v1 is the same as v1 times u1. And I'll do a similar thing with the other piece. And then by the definition of a dot product, this must have been vector v times vector u. And then we're done. Yes. Yeah, no problem. Well, I mean, it's a problem, but no problem going to IT right now. Understandable. Does that make sense what we did there, Tomasino? Yeah. And in general, this is the first step for any, 23 through 28 is to just write them in component form, do the operation in component form, do some switcherooing with the components, and then go back out into vector form again. What else from homework do we guys have? Do you guys have more questions? Okie dokies. If nobody else has anything, we're going to go ahead and grind out our last section here in Chapter 8. This is about 2D vectors in space. All right. So what we're going to be doing in section 8.4 is we're going to introduce another notation for vectors and use that notation to write vector equations for a line. And we'll do the same thing that you would have done in your Algebra 2 class, looking at whether two lines are like parallel or intersecting and what's their intersection, and or if they're perpendicular, or not perpendicular, coinciding. So we're going to be doing that same kind of idea, just with vector line equations instead of linear equations. So that's kind of where we're going. So we'll start off by just introducing a new notation. So this new notation is called IB component form, or when I was a student, we called this a column vector. Because it was written vertically like a column in a matrix. Notice that ostensibly there is no difference here between the component form we've been dealing with and this. It's just visual, right? Instead of writing it horizontally, we're stacking it vertically and using a parenthesis instead of a wedge. Oh no! I find the hardest thing about this, writing a vector this way, is remembering not to put a, to do that and make it into a fraction, which my every instinct wants me to do as soon as I start writing numbers vertically. But it's not a fraction. Make sure that you're not including that. So what I want to do is I want to now write a vector equation for a line. So you remember back in like Algebra 1 or earlier, you would have written an equation for a line. One way you could do it is like y equals mx plus b, right? Everybody's okay with that? Where the x and y were the coordinates for the point in your line. So our vector equation for a line we're going to write in the following way. We're going to write R equals VT plus R naught. So vector V we call our slope vector. And vector R naught could be any point on the line y equals mx plus b. And then R is going to be like a vector coming out of this. So, worth noting here, remember that slope is like change in y over change in x, right? And regardless of whether m is written as a fraction or just a regular old number, you can always think about it as a fraction just by making a denominator of 1 if it doesn't have one. So if I convert my slope into a slope vector, the x component is on top, so the change in x should be on top, and the change in y should be on bottom. So notice that it's like the flip-flop of the slope fraction, right? Does everybody feel okay with what we've done? All right. Let's do an example now of going back and forth between a linear equation and a vector line equation. I guess before we start, notice that this says a possible. There's going to be infinitely many correct vector line equations for any given line, because R naught can be any point on that line. And really, I could put like a scalar on here and it's really the same slope, right? Because if this is like Ka over Kb, that's still the same thing as A over B, right? Still the same slope. So there's like infinitely many different ways I can represent this, just as an aside. So first thing I'm going to want to do to get the vector line equation is I need the slope off of this line and any point on this line. So what's the slope for y equals 3x plus 5? It's 3. But I need to write that as a fraction, so how am I going to write it? 3 over 1. So that means that my slope vector can be 1, 3. Feel good so far? Then I need a point from the line y equals 3x plus 5. What's the easiest point to get? Usually the y-intercept, right? Because it's staring us right at the face. What is the y-intercept here? For the line y equals 3x plus 5. Zero, 5, right? Does it have to be that one? No, but great, good googly moogly, it's like sitting right there. All I do is 0, comma, whatever were added, right? So that's going to become the vector R naught 0, 5. Again, remember, it's x, y is our stack. So my vector equation for the line then is going to be R equals 0, 5 plus VT. Does that feel okay as to how I did that? Yeah. Yeah, sure. Okay. Let's go the other direction now. Let's take this vector line equation and create a slope-intercept equation. So I'm going to start by identifying the slope vector, which is the one attached to the t. So in this case, my slope vector is the vector 2, 3. So my slope should be 3 over 2. Again, just a flip-flop of it. Everybody okay with that? Next, I'm going to identify my point vector. That's the vector 3, negative 1, which tells me the point I have a point on this line, 3, negative 1. To write the slope-intercept equation with a point and a slope, I'm going to go ahead and plug this in as an x and a y. So I -1 equals 3 over 2 times x plus b. And now I'm just going to solve this for b, and I have everything I need, right? And let's just make that a common denominator. So -1 I'll just make as -2 over 2. So when I subtract the 9 halves over, I get b is -11 over 2. And now I have everything I need. I have my slope and my y-intercept. Everybody feels okay there? Okay. All right. So any two lines have to be one of three things. They either have to intersect, they have to be parallel, or they have to be coinciding. When I say coinciding, it means like they overlap completely. Like that's the infinitely many solutions when you solve a system of equations. You remember that from Algebra 2? Okay. So I know if two lines are intersecting, they have to have different slopes. Right? If they're parallel, they have to have same slope. And the same thing with coinciding, they have the same slope. The differences between parallel and coinciding, parallel lines have no points in common. And coinciding has every point in common. Everybody's okay here? So the way that I'm going to say I have two lines, L1 and L2, and I want to check to see if they are intersecting, parallel, or coinciding. So the first thing I'll ask is, do they have the same slope? If the answer is no, then I'm done. I know that they're intersecting. And then I'd be left with finding the intersection. If they're yes, I have to check then to see if they're parallel or coinciding. So I'll ask, is a point on L1 also on L2? If the answer is yes, then they're coinciding. If the answer is no, then they're parallel. Does that feel okay to everybody? So what I'm going to do now is adapt this so I can do it for vector line equations. Okay, so I'm going to draw basically the same structure, but I'm going to write these tests now, instead of in words, symbolically for what we're going to be doing if we have L1 and L2 as vector equations of lines. Is everybody okay with that? Okay. So let's say I have R1 equal to R01 plus V1t, and then R2 equal to R02 plus V2, and then I'll use a different letter, I'll use S. So these are my two vector equations for lines. The first thing I want to do is check to see if they have the same slope. So what I want to do is I want to see, is K times V1 equal to V2? If the answer is no, then I know they're intersecting. And to find that intersection, I'm going to take R1 and set it equal to R2. And we'll do examples of like doing this with you guys here. If they have the same slope, then I know that they're either intersecting, or I'm sorry, parallel or coinciding. So I have to say, is there a point on R1 that is also on R2? So what I do is I say, okay, take R01 and I set it equal to R2. So if it's yes, they're coinciding. If it's no, then they're parallel. So let's go through and do some specific numeric examples where I use this diagram to help me sift my way through. Sound good? On top of the file cabinet. I got a whole box. You are welcome to help yourself. Since you live so far away from it, maybe grab a couple if you think you're going to be making more than one trip so you can save yourself the steps. Yeah, you're welcome. Oops. That's not what to do. All right. Let's say we have this R1 and this R2. Okay? So the first thing we check is, do they have the same slope? To do that, I take the slope vector from R1 and check to see if it's a scalar multiple of the slope vector from R2. So basically what this is saying is 1 times k needs to equal 3, and 3 times k needs to equal 5. Is everybody okay with how I came up with that set of equations? Now, if 1 times k is equal to 3, k is equal to 3. But if 3 times k is equal to 5, k has to be 5/3. Those disagree, correct? What that tells me is the answer to this question is no. They are not the same slope. That's what the not equal to is telling me. If I got the same value for k, then those are the same slopes. So far, so good? Okay. So next I'm going to check, is there a point from R1 that is on R2? So I'm going to grab a point from R1. The obvious point to choose is the vector 2, 4. Is everybody okay with how I built that equation? You see the pieces that went together? Trying real hard to color code this. So what this equation is saying then, 2 has to equal -1 plus 3t. And 4 has to equal 5 plus 5t. Is everybody okay with how I wrote those? I'm now just going to solve each equation for t separately and see if they have the same t. Is that okay? So the first equation, I'm going to add the 1 over. And the second equation, I'm going to subtract the 5 over. So there I have t equals 1. And there I have, wait a minute. Gosh dang it, guys. I'm doing the wrong end of my diagram, aren't I? I said no. I'm over here now. Look what I'm doing. How come you didn't stop me? Mr. Kulik, you're better than this. Come on now. I'm sorry, guys. Okay. My apologies. My apologies. I was just an example ahead, okay? All right. So we said no. So we have to find the intersection then. My apologies, guys. All right. So to find the intersection, we say R1 has to equal R2. So I take 2, 4 plus 1, 3s equals negative 1, 5 plus 3, 5t. Everybody good as to where I pulled the pieces from? All right. So what this says is 2 plus 1s has to equal negative 1 plus 3t. And 4 plus 3s has to equal 5 plus 5t. And now I'm just going to solve this system of two equations. Everybody's okay? I'm going to show you how to do this on your solving the system on your calculator so you don't have to do it by hand. You're welcome to use substitution or elimination if you want to. But I'm going to show you a way to do it on your calculator that'll just give you the answer and with no fuss, no muss. Everybody good? To be able to do this on our calculator, though, my set of equations has to be formatted a certain way. So I have to have like the s's and t's on both on one side, and then the constant on the other side, and the s's and t's have to line up vertically. So for the first equation, I'm going to subtract 3t from both sides and subtract 2 to the other side. And then on the second equation, I'm going to subtract 5t from both sides and then subtract 4 to the other side. So now you see everything lines up vertically, right? Now that I have my set of equations, so they all match up, I can now solve this system entirely on my calculator. So I'm going to press second and then the matrix button. That opens up the matrix menu. From the matrix menu, I'm going to go over to the Edit tab. And I'm going to select one of these matrices. So I picked matrix A. The first thing I'm going to do is change the dimension of my matrix to match the dimension of my equation. My system here has two equations, so I need 2 rows to my matrix. So the first number should be 2. And my system has a column for t's, a column for s's, and a column for the answers. So I need 3 columns. So I need 2 by 3. Now I'm just going to type in the coefficients for each equation. So negative 3, 1, negative 3, and then negative 5, 3, 1. Is everybody okay with how I got that in there? I'm now going to exit out to the main screen, press second in mode. I'm going to go back to the matrix menu, so second and matrix. This time I'm going to go to the Math tab, and I'm going to scroll down until I find the command RREF. Now be careful here because there's also a 1REF. You want to make sure you're picking 2REF. Okay, so RREF. And then I need to go back into the matrix menu for the last time, staying on the names tab, and I'm going to pick that matrix A that we just built, close my parenthesis and press enter. So what this first line reads, it says 1x plus 0y is equal to 2.5. I should say 1t plus 0s is equal to 2.5, or just t is 2.5. Yes, you may. And if I look at the second line, this says 0t plus 1s is equal to 4.5, or just s is 4.5. So far, so good. This is not my point, though. This is just the key to get me my point. So now I can take either answer. It does not matter. For the sake of argument, I'm going to pick the t, and I'm going to plug that back into R2. And so when I crunch this down, I'm going to get 7.5, 12.5. That's just me doing 3 times 2.5 and then 5 times 2.5. And then if I add those two vectors, that's going to be 6.5, 17.5. So I should have the point 6.5 comma 17.5. Everybody feel okay there? Let's do another. Let's say that our vectors are let's not do that there. Do that. Actually, I'm going to do that. There we go. So let's say these are two vector equations for lines. First question we ask is, do they have the same slope? So I'm going to take the slope vector from R1 and see if it's a scalar multiple with the slope vector from R2. So I'm asking myself if negative 2k needs to equal 3 and 4k has to equal negative 6. So that tells me k is equal to 3 over negative 2, or that k has to equal negative 6 over 4. I notice negative 6 over 4 reduces down to negative 3 over 2. So those are the same k, correct? So my answer here is yes. So I need to ask now, is a point on R1 also on R2? So I'm going to take a point from R1 and see if it's equal to R2. Are we okay with what I've done here? So my system will be 2 equals negative 1 plus 3s, and then 3 equals 5 minus 6s. I'll solve each of these equations for s and see what I get. So if I add 1 to both sides and then divide by 3, I get s is equal to 1. If I subtract 5 from both sides and then divide by negative 6, I get s is equal to 1/3. So the answer to this question, since those are not equal, is no. So that tells me then these lines are parallel. Does that feel okay? If the s's were equal, what would that tell me? Coinciding, right? If those two happen to be equal, they would be coinciding. What do you guys say? Is this okay? Do you want to do more examples, or do you think you kind of get the idea? All right. So for your guys' homework, I'd like you to do 51 through 54, 59 to 62, and then 73 to 76. And let me update the assignment here for that real quick, because I think I had more problems than that included, but I don't think I really want to include all of them. Oh, I haven't made it yet. Perfect. Yes. Yes. Okay, so as a reminder, this set of problems won't be due until the 26th. For this Sunday, we had 14 to 50, and then the delta math. But really, let's be realistic. Mr. Kulik isn't checking work on Monday when we don't have school. So you'd really think about this as like due Tuesday, and Mr. Kulik won't know the difference. Does everybody feel okay as to what's due, when it's due, what we've been doing? This is the last section in Chapter 8 that we're doing. Guess what that means? Yeah, so next week we're going to have the review day and then the test day. As you're doing your homeworks, I would think about starting to get my half sheet of notes together. So as you're doing your homework and you have to look things up, make sure you take a look at or start putting a half sheet together. If you look at the review, these formulas that are on the end of the review, these are the formulas that I'll give you on the test, so you don't have to include those. But if there's other stuff you want to include, like example problems or other definitions or whatever, I would make sure I start doing that. Somebody asked me the other class in 4th hour about like these different forms of vectors, and I made this vector diagram of like these different names of vectors and how to convert back and forth between the forms to organize that information a little bit differently visually. So I put that into the OneNote if you're interested in that. That's there. And I'll get you a test description up here. Probably by the end of the day, I'll have some kind of test description for you on the OneNote also. Any final questions for me? Everybody clear as to what's coming up and what to do when? Okay, you guys got 40 minutes or so. I would start cranking away on your problem set or finishing up your delta math. If you haven't done that yet, you could work on that. Either is fine. Go ahead, Maddie. You're welcome.